In the last lecture, we have seen the concept of a simply ordered set, the concepts of supremum, infimum, upper bound and the least upper bound, and also the concept of a linear continuum. And we defined the order topology with respect to the simple order, and our theorem that we stated in the last lecture was that a linear continuum is connected in its order topology. And we will prove this theorem in this lecture, and in fact we will prove something a little bit stronger. So let me write it as another theorem. So it says that any convex subset of a linear continuum is a connected subspace in the subspace topology coming from the ordered topology. So what is a convex subset? So a set A, which is a subset of L, is called convex. So like this is a definition, is called convex if for any A and B in A we have the set AB, which is just the collection of points in A such that either x equal to A less than x less than B, or x or x equal to B. So this is the usual closed interval in R, and we have generalized it to a simply ordered set. So for any AB in A, we have this entire closed interval must be a subset of A, and we are saying that a convex subset of a linear continuum is a connected subspace, which means that when you define the order topology on the linear continuum, and with respect to the order topology you give the convex subset subspace topology, then it becomes a connected subspace. So let us see a proof of this theorem 4.2, but before that we can already have as a corollary. So the first corollary that we have is that any interval, so any interval of the form AB where A is less than B in L is a connected subspace, and also we can define any ray which is of the form A, we denote it by A infinity, and this is simply the set of all points in L such that A is less than x. Any ray is connected. So by the way, a ray can also be on the other side, so we can also define minus infinity to A, which is the collection of all points such that x is less than A. So both these are called rays, and any ray is connected. And we have already seen that a consequence of this theorem or this corollary is that we can write it as another corollary, is that any interval or ray in the real line is a connected subspace, and in particular R itself is connected. connected. Of course, we are taking the ordered topology, which is the same as the standard topology. Standard topology, R is connected. So now let us go back to the statement of the theorem 4.2, and we want to show that any convex subset of a linear continuum is a connected subspace. So let us see a proof of theorem 4.2, and we will again argue by contradiction. So suppose that Y is a convex subset of L, and Y is not connected. So this means that there exists a separation AB of Y. So AB non-empty, disjoint, and A union B is the whole space Y, and A, B are open in the subspace topology of Y. So this is a separation for Y, and now let us take a point A in A and B in B. This is possible because both are non-empty. So this means because Y is convex, that the closed interval AB is a subset of Y. Now if we take the intersection A0 of A with AB and B0 of B with AB, then they are open. A0, B0, they are open, they are non-empty, they are disjoint because A and B are disjoint, and their union is the whole space AB. So then this means that A0, B0 is a separation of AB. So these are both open in the subspace topology of this set AB. Okay, so this is the subspace topology on AB from the ordered topology on L. So now we have a separation A0, B0 of AB. Now let's suppose that C is the supremum of the set A0. So C exists because B, since B is an upper bound for A0. This is simply because A0 is a subset of AB and B is the largest element of AB. So by the least upper bound property, so by the least upper bound property, C exists. Okay, so we have at least one upper bound, and so this point B is an upper bound for A0, and so the set of upper bounds is non-empty. and therefore it must have a least upper bound by the assumption on the linear continuum. So we have this point C, and now we will show that C does not belong to either A0 or B0, which is a contradiction, since the union of A0 and B0 is the interval AB, which is a contradiction, since first of all C must belong to AB. Notice that B is an upper bound, so C must be less than B, and C is greater than A because A belongs to A0. So C belongs to this set AB, and AB is the disjoint union of these sets A0 and B0. So if C does not belong to either A0 or B0, then we have a contradiction. So we take these two cases one by one, and we will show that they are both false. They both lead to contradiction. So now we take these two cases one by one, and we will show that they both lead to contradiction. So what are the cases? So case 1 is that C belongs to A0. So if C belongs to A0, then C cannot be equal to B, since B is in B0 and A0 intersection B0 is empty. So C cannot be equal to B. So this means that then A is less than or equal to C, or which is strictly less than B. Now since A0 is open in this set AB, so there exists an interval. So this is a basis set for the order topology, basis element for the order topology on L. So this will be of the form DE or CE, so containing C, and either of these sets DE and CE will be a subset of A0. So here note that we have D less than C less than E. Okay, so we have this basis element because of the openness condition. We have the basis element containing C, which is contained inside A0. But by the second property of the linear continuum, but by property 2 of the linear continuum, there exists a point Z in A0 such that C is less than Z is less than E. So just taking a point in this intervals which is strictly greater than C and strictly less than E, by the property 2 of the linear continuum, we find such a Z. But now this is already a contradiction, because we have found an element Z of A0 which is greater than C, but C was supposed to be an upper bound of A, of A0. So this is a contradiction. This is a contradiction to the fact that C is an upper bound of A0. So in particular, A is less than C for all A in A0. So let me write it as something else, because A was something already chosen. So x less than C for all x in A0. So this is a contradiction, and so we see that C cannot belong to A0. So now we come to the second case, case 2, which is that C belongs to B0. So let me draw a quick picture for the first case. So here we had A, here we had B, and they set the point C was somewhere here or somewhere here. Okay, and if C was strictly greater than A, then we can choose a basis element like this, and if C is equal to A, then we choose the open interval C to E with C included. Okay, so this was the first case. In the second case, we have C in B0. So in this case, C cannot be equal to A, again because A is in A0, and A0 and B0 are disjoint. So here C is either at the point B or somewhere here in the middle. So again we can take so since B0 is open in AB, we can take an interval dB such that C belongs to dB, and this is a subset of B0. So here we have this D is here and it contains C, but this implies that, this means that the interval DC cannot contain any point x of A0. Why? Because then we will have a common point in of A0 and B0. So then that would imply x will belong to A0 intersection B0. So this is a contradiction. So this interval DC cannot contain any point in any point of A0. So D is, this implies that D is an upper bound of A0 which is strictly less than C, and this is a contradiction to the fact that C is the least upper bound of A0, which is a contradiction to the fact that C is the least upper bound for A0. So in both cases we see that C does not belong to A0 or C does not belong to B0, and this we have seen that this leads to a contradiction, because the whole interval AB is the union of A0 and B0, and C belongs to this interval. So this proves our result that a linear continuum, any convex subset of a linear continuum is a connected subspace. And this from this result, our main theorem, which was theorem 4.1, let me go back there. So the first result we wanted is the linear continuum is connected in its order topology, because a linear continuum itself is convex. Because of the second property of the linear continuum, it is always convex, and therefore a linear continuum is connected in its order topology. So we have these corollaries. So corollary is that a linear continuum is connected as it is convex. So this is by the second property of the linear continuum, and also that the real line is connected as it is a linear continuum. So we have now proved that the set of real numbers with the standard topology is a connected set, is a connected space.